Hello everybody and welcome to Electric Fields Lesson 3. In this lesson we're going to be exploring concepts such as electric potential energy and electric potential, and eventually we're going to look at how we define and how we can calculate potential difference from an electric point of view. Now obviously potential difference is a phrase that you've heard before both at GCSE and at year 1 of A-level, but you've never really had a definition before, so hopefully by the end of this lesson you'll understand more about what potential difference really is and how we can calculate it with respect to electric fields. Firstly though, just a recap of last lesson. Last lesson we looked at electric field strength, and there's the definition from last lesson. From the definition we had the equation E is equal to F over Q, where Q is the charge of a small positive test charge. Using that equation we derived a couple of other equations. Firstly, the electric field strength for a radial field, which was E is equal to Q over 4 pi epsilon naught r squared, and we also derived an expression for a uniform electric field, which was E is equal to V over D, where V was the potential difference between two parallel conductors. So on to today's lesson then. The first thing we're going to look at and study today is the idea of electric potential energy. Now on the screen I've got two charges. I'm going to make them both positive for now, just to make life easy. We know from previous lessons that there will be a force, and that will be a repulsive force, acting on both of these charges. And that force will be acting in the direction drawn on the screen. What we're going to do then, in order to get an idea of potential energy, is we are going to fix this left-hand charge in place. So we're not going to move that at all. We're then going to take the right-hand charge and we're going to move it from the position it's currently in, and we'll move it into some other position closer to the charge that we fixed. That distance we're going to call delta R. Now because we're moving that charge closer to the fixed charge, more importantly we're moving it in the opposite direction to the force that would be acting on it, that force of repulsion from the fixed charge. In order to do that then, work must be done on this right hand charge in order to move it closer. The work that's being done, of course, is work done against that electrostatic force that we studied a couple of lessons ago. Of course, if we had two negative charges, then work would be done in exactly the same direction. We would still have a repulsive force acting between these two charges, and therefore in order to move it closer we would have to do work. If we had two opposite charges, a positive on the left and a negative on the right, or vice versa, then the work done would be in the opposite direction. The force would be attractive, and therefore we would have to do work in order to move it further away. Either way though, back to what we're looking at the moment, we have to do work in order to move the right hand charge closer to the one on the left, work done against that electrostatic force. From mechanics last year we know that work done is force times distance in the direction of the force. The way that we've drawn this diagram, theta is 0 and therefore cos theta will be equal to 1. We can therefore discount it from our equation, and we're just left with W is equal to F times S. We can now start plugging terms into this equation. we have, for force, Coulomb's law, Q1, Q2, over 4 pi epsilon naught r squared. We might as well label the left hand one as Q1 and the right hand one as Q2 in order to save the confusion there. And our displacement, the way that we've defined it here, is delta R. Our equation for work done therefore becomes Q1 Q2 over 4 pi epsilon naught r squared, there's Coulomb's law, and we're going to multiply that by delta R, which is the distance that we've moved. Now I'm going to cheat here a little bit. I'm just going to cancel this delta R with one of these R's down here. Now that's probably the best I'm going to be able to do without going too much into the maths behind this. I suppose in theory what we should be doing, for those of you who are doing further maths and are starting to really get a handle on this, what we should really be doing, if we're going to be really pure about it, is integrating f with respect to r and doing it that way. But that kind of mathematical approach is way beyond what we're supposed to be doing with this course. If you are good at maths, you might want to do that yourself, just integrate over that distance. But for now, all we're going to do is we're going to cancel the delta R with one of the R's on the bottom of the force equation. What we're left with as an equation on the right hand side of the equal sign is now this, Q1 Q2 over 4 pi epsilon naught r. Note it's just r here and not r squared. What I'm now going to do on the left hand side is I'm going to label that as potential energy, E with a subscript P. We know we can do that because from a dimensional point of view, both work done and potential energy both have the unit of joules. So now what we're left with is an equation for electric potential energy, and that will be the electric potential energy at a certain point. Mathematically, of course, what we can do is we can work out what the electric potential energy is where we started our charge, and we can work out what our electric potential energy is when we finished moving our charge. And the difference between those two energies will be the same and will equal the work done that we were trying to calculate in the first place. Now, if we consider a new idea, electric potential, we will work this through into potential difference on the next slide. If we have a look, we've got the definition on the screen. So the electric potential at a point in an electric field is the work done per unit charge in moving a small positive test charge from infinity to that point. Now, at the moment, that might look quite complicated. And there's probably a few things that scare you in there, but there are also some familiar terms as well. Firstly, we come back to this idea of a small positive test charge, and that's exactly the same as we looked at in the last lesson. Secondly, we can also see in the definition the term work done. We've just on the last slide calculated or derived an equation for work done, so hopefully the next stage should be relatively easy. Now, if we take this definition a little bit further, let's go back and let's redraw in a positive charge, and this is the positive charge that we are studying. Over here I'm going to draw our small positive test charge, and that small positive test charge will be at a distance r is equal to infinity away from the charge that we're studying. What's significant about that point infinity then? Well, if we go back to Coulomb's law, let's just redraw it on again just to remind ourselves. F is equal to Q1 Q2 over 4 pi epsilon naught r squared. At that point, if we were to plug r is equal to infinity into this equation, then, well, infinity squared, what is infinity squared? That's probably a subject for another day, or something to annoy your maths teachers with. Either way, what we're going to end up with is infinity on the bottom, and therefore our force at that point infinity, at an infinite distance away, the force will equal 0. There will not be any force acting. And in fact, as long as r has a value less than infinity, f will still have a value above 0. No matter how large r might be and how infinitesimally small f might be, at least mathematically, until we get to infinity, f will still have a value, and it will only ever become 0 when we get to infinity. What the definition of potential then says is that we're going to take that small positive test charge and we're going to move it from infinity into some point, some other point that is not infinity, and at least there we should be able to measure what that distance r is there. What the equation says then is work done per unit charge. We can now start to form an equation for the potential at this point. Work done per unit charge means W over, and we're going to use little q here for charge because we're talking about the charge of our small positive test charge. And that will equal the electric potential. The symbol for electric potential is a capital V, and electric potential takes the unit of volts, as we've seen before when we've been doing electric circuit theory. Now if we have a look at the units on the right hand side, the unit of work done we know is joules, and the unit of charge is coulombs. So we can therefore say that the SI equivalent of the volts is joules per coulomb. Now that I've written the equation like that, V is equal to W over Q, hopefully that won't be that much of a shock to you, because that looks very similar to the equation that you would have come up with and you would have derived back in year 1 when you were looking at potential difference as far as circuits go. What we're now in a position to do is to plug in the equation that we had on the last slide for work done into this, and to come up with a more specific equation for electric potential. And we end up with this. V is equal to Q1 Q2 over 4 pi epsilon naught R. That was the equation from the last slide. And we're going to multiply that by the 1 over Q, so that's the same as dividing by the charge of the small positive test charge. That small positive test charge will cancel out with one of our charges on the top of the equation, and what we're left with is V is equal to Q over 4 pi epsilon naught R. And that's our equation, or at least one of our equations for electric potential. Before we move on, it's worth noting that electric potential is a scalar. It is defined from work done, which is also a scalar. So before, in the last couple of lessons, we've been dealing with force and we've been dealing with electric field strength. Both of those are vectors. Here, in today's lesson, we're taking electric potential energy, which is a scalar, and electric potential, which is also a scalar. Now, not this lesson, but next lesson, we're going to look at how mathematically we need to treat potential as a scalar different to how we would treat electric field strength or force from Coulomb's law, those being vectors. There is a subtle difference in the mass behind that, and we just need to make sure that we can fully understand that. Finally then, we can come on to this idea of potential difference. What I'm going to do, I'm just going to take a generic charge Q. I'm not going to bother putting a sign on it yet because it makes absolutely no difference to the theory that we're going to look at the moment. From the last slide, we know that we can take a point some distance away, R, and we can calculate the potential at that point using the equation Q over 4 pi epsilon naught R. If we were to take a second point a different distance away, we can also now measure the potential at this point. And just to make things clearer, I'm going to call the blue one V1 and therefore R1. The first point, I'm going to call this one V2 and R2 the second point, where R2 is that distance away. So it's the distance away from the charge. Well, if we think about potential difference, we have the word difference in the title, and difference just means one thing subtract from another thing. Because we started at V1 and we are moving to V2, we will have a change in potential, delta V, and therefore a potential difference. Whenever we're using delta and whenever we're calculating anything with delta, we are always going to take the final value and we're going to subtract from it the initial value. So in our equation here, delta V becomes V2, that's our final value, minus V1, that's our initial value. And there finally we at least have an idea of what potential difference is. We can calculate the potential at 2 points. The potential difference will therefore be the difference in potential between those 2 points. What we now need to do then is look at how we can use the idea of potential difference in other equations. If we go back to the last slide, we had the equation V is equal to W over Q, the work done per unit charge. Now, if we were to multiply both sides of that equation by little q, we end up with this equation, delta W is equal to Q delta V. Now, I've just thrown the deltas back in there. The reason why comes back to the idea that we were looking at before and discussing before about really having the need to integrate on both sides of our equation and going into that level of maths. So for now we'll just put the deltas back in. Again, if you want to have a look at the integration side of things in your own time, you are more than welcome to. Therefore, by using this equation then, we can calculate the work done. If we know what the potential difference is, and we multiply it by the charge of the charge that we're moving, the small positive test charge, or however you wish to term it, we can therefore determine the work done in doing that move. If now we go back to this original diagram and start to think about what's happening, let's now call this positive Q and have a look at what's going on with the positive charge, and we'll make this again a small positive test charge as well. Because the main charge that we're looking at is positive, then both V1 and V2 will both have positive values. Because R2 is greater than R1, R2 and R1 both being on the bottom of the equation will mean that V2 is smaller than V1. Because V2 is smaller than V1, if we come back to our delta V equation, we're subtracting V1, which is bigger than V2, from it. What we're going to end up with then is that delta V will end up as a negative value. When we put that negative value back into the equation, delta W is equal to V delta Q, well, delta V is negative. Q, our test charge, is positive. And we know from basic maths that a positive multiplied by a negative will also give us a negative. Now hopefully that confirms what we said a couple of slides ago when we said that we would need to do work in order to move the charge in this direction, in order to move it closer. Positive work would have to be done in that direction, so delta W would have to be positive, moving in that direction. What we've done on our diagram is to move it in the opposite direction, and therefore delta W would be negative. Exactly the same arguments are going to apply if we make both the charges negative as well, because the force will still be repulsive. Let's though obviously try not to make the diagram too complicated, but let's have a look at what would happen if we had two opposite charges. So if we had negative Q as our main charge, but we kept our test charge as positive Q. Well, in that situation, what we would end up with is an attractive force. The force would be attracting the test charge to the left as we've drawn it in the diagram. What we would therefore have to do is we would have to do work in order to move it further away, and therefore if we're moving that charge to the right, we would fully expect delta W to be positive at that point. Let's now look at putting this into practice. So here is your question for this lesson. Two positive point charges of 12 and 8 microcoulombs respectively are placed 10 centimetres apart in a vacuum. Calculate the work done in bringing them 4 centimetres closer. As usual, pause the video, have a go yourself and come back when you think you've got an answer. So in order to look at this question then, I'm going to firstly draw the plus 12 microcoulomb charge here, and we're going to say that this is our fixed charge, so we're going to keep that in position and we're not going to move it at all. We're taking our plus 8 microcoulomb charge and we're moving it from 10 centimetres away to a point 6 centimetres away. That's the 4 centimetres closer bit that we're covering. We're starting here, so I'm going to label that as V1, and in a moment we're going to calculate the potential at that point. We've moved it to here, so I'm going to label that V2, and we can calculate the potential at that point. In order to calculate the work done, we're going to use delta W is equal to Q delta V, where little q here is going to be our plus 8 microcoulombs. The next stage then is to calculate the potential difference delta V. So we know that delta V is V2 minus V1. We can expand that out to say V2 is Q over 4 pi epsilon naught R2, and that will be 6 centimetres when we put that in. And we subtract from that Q over 4 pi epsilon naught R1, which is our initial position and therefore is 10 centimetres. The Q on the top of the equations here will be the 12 microcoulombs that we'll plug in just a moment's time. What we can see first though is that in both of these terms, Q over 4 pi epsilon naught R2 and Q over 4 pi epsilon naught R1, the Q, 4 pi and epsilon naught are all like terms. So just to neaten things up, I'm first going to write this as Q over 4 pi epsilon naught, which are our like terms, and we're going to multiply that by brackets 1 over R2 minus 1 over R1. We can now start to plug some numbers into the equation. So on the top we have 12 times 10 to the minus 6 divided by 4 pi epsilon naught, 4 pi, multiplied by 8.85 times 10 to the minus 12. And we're going to multiply that by 1 over, well, R2 is 6 centimetres, 0.06 metres, and we will subtract from that 1 over R1, so that's 10 centimetres, and therefore 0.1 metres. What your calculator will hopefully tell you at that point, once we've rounded to 3 significant figures, is we should have a potential difference of 719 kilovolts. It's quite a large potential difference, but we'll soon see how the numbers will work themselves out in a moment. We've now got our potential difference, 719 kilovolts. In order to calculate the work done, we come back to our delta W equation. Delta W is 8 microcoulombs, so 8 times 10 to the minus 6, multiplied by 719 times 10 to the 3. Now, of course, in my calculator, I'm going to use the exact answer rather than use the rounded answer. What we should therefore get as a final answer for delta W, and we will obviously round at this point to 3 sig figs, is 5.75 joules. And there's the answer, so 5.75 or 5.8 depending on how you've decided to round. So in summary today then, we've looked at 3 different concepts. Firstly, we've looked at electric potential energy, and we have the equation EP is equal to Q1 Q2 over 4 pi epsilon naught R. For electric potential, we have the definition: electric potential at a point in an electric field is the work done per unit charge in moving a small positive test charge from infinity to that point. Now, I didn't mention it earlier, but that definition, unfortunately, you will have to remember. That is usually a favourite of AQA to make you give that definition, normally for 2 or 3 marks in an exam paper. Our potential then was work done per unit charge, but then we got the more specific equation of Q over 4 pi epsilon naught R. Finally then, we looked at potential difference, and we came up with the equation delta V is equal to V2 minus V1. The final thing just to remind you of is that both potential energy and potential are both scalars, and as I said, next lesson we'll have a look at how mathematically we can treat scalars and vectors differently, and how we need to treat them differently. Now, that is quite an abstract concept, looking at potential energy and potential. I suggest you maybe watch this video a couple of times, and obviously look in the textbook as well, in order to really get a grasp of what electric potential is. So, as usual, thank you very much for watching. I hope you enjoyed that video and got something useful out of it, and I'll see you in the next video.